Hi, we're Team 23060 and we are airplane controls for Armless Pilot. Our sponsor is the Right Footed Foundation and our advisor is Dr. David Margales. Hi, I'm Simon, I'm the team lead.
My name is Zachary Thatcher, I'm the procurement lead.
I'm Alejandro Lopez, I'm an aerospace engineer.
My name is Renato Ramos, I'm also an aerospace major.
My name is Shihab Zaman, I'm an electrical engineer.
So before we get started, I just wanted to go over some information about airplane anatomy. As you can see here, at the back of the plane, you have a tail made up of stabilizers. On the horizontal stabilizer, you have the elevator, which controls the pitch of an aircraft. On the wing of the plane, you have the aileron, which controls the roll of the plane. On the vertical stabilizer, you have the rudder. This controls the yaw of the plane. Our sponsor, the Right Footed Foundation, is composed of Jessica Cox and her husband Patrick Chamberlain. Jessica is best known for becoming the world's first armless pilot. She currently flies an aircraft called the Air Coupe. In this aircraft, the rudders and the ailerons are interconnected, so this means that there are no rudder pedals, and you can use the yoke to control all 6 degrees of freedom of the plane. The Air Coupe does have its issues. The Air Coupe cruises at about 90 miles an hour, so long journeys are quite slow. Most important, the Air Coupe is very uncomfortable for Jessica to fly for a long period of time. With her right foot on the yoke and her left foot on the throttle, it is similar to doing a crunch for a long period of time. On long flights, her legs will cramp up and her feet tend to fall asleep. This is why Jessica partnered with Vans Aircraft to design the Impossible airplane, the airplane that will be the world's first foot-controlled airplane. To do this, Jessica is modifying an RV-10. The RV-10 is a much faster and more modern aircraft that will allow Jessica to be in a far more comfortable position while flying. However, there are some obstacles that Jessica currently faces with the RV-10. The RV-10 uses a control stick and the rudder pedal for flight control. This makes it extremely difficult and unsafe for Jessica to fly the RV-10 while also maintaining controls of the navigation system, the communication system, and the throttle. Our goal for this project is to design a control system that will allow Jessica to safely pilot the RV-10.
Our system requirements were split into 3 categories: performance, design, and safety. I will be going over the requirements which are highlighted. The system shall operate ergonomically within the capabilities of the pilot. The system shall allow the plane to have full range of motion for the elevators, ailerons, and rudders. The system shall meet FAA regulations. The system shall not interfere with co-pilot controls. To fulfill these design requirements, we considered multiple trait designs. Some of these were the Austin control system, a previously designed system that had mechanical flaws, a leg extension system, and a 2D cross system. Finally, our team came up with a design that we felt best fulfilled our design requirements. A 2-pedal system that would control all 6 axes of the plane with just 1 pedal. We called this idea Airplane Pedals for Pilots Without Arms, or APA. This system allows the pilot to control the plane with 1 foot while using the other foot to operate other controls such as radio, navigation aids, and the throttle. In the event that more force is required to operate the plane, the pilot can use both feet on the pedals to reduce the required force in half. This design also provides the pilot with a way to rest their feet and reduces the likelihood of getting Charlie horse or any muscle fatigue. In addition to this design provided us with the most amount of intuitiveness. The reason why the design must be intuitive is so that very little training is required and pilots are able to make split-second decisions when flying.
As mentioned before, to keep the design intuitive, we wanted our pedals to have the same linear motion as the rudder pedals in the RV-10. This was accomplished by placing our pedals onto a railing system. We first mounted the rails to the floor of the RV-10 and then mounted our pedals on the carriage, creating the sliding motion that we wanted. We then created a linkage system that would directly connect the rudder pedals on the plane to the APA. This was done by creating a peg and placing it on the rudder pedals. We then added a pin joint at the bottom of the peg and another pin joint on the carriage of the APA and connected the 2 pin joints with the link. This combination of linkage and rails gave us a range of motion of about 4 inches forward and 4 inches back.
So now for the elevator mechanism, we created a linkage system similar to a double rocket mechanism. So if you lift up the pedal about 20 degrees, it will cause the elevator push rod to rotate about 30 degrees, which then will Through a series of linkage, we'll rotate the elevator about 30 degrees up and down. This 30 degrees satisfies our movement system requirement. In addition to this, we performed a force analysis to determine that 22.22 pounds is required to use the elevator. One innovative aspect of this design is that in order to incorporate the aileron, the elevators, and the rudders all into one pedal, the linkage features a sliding joint that leaves plenty of room for the rudders to complete the full motion, and it also leaves plenty of room for the elevators as well.
We want to talk about the ailerons and how to reduce the force with our push rod and slider movement. For our system requirement, we want to use 1.2, which is the system shall reduce the amount of movement required to operate the plane. We want to use 32 degrees left and right of swivel movement because that's how much it takes to operate that aileron from its min to max position. We also want to reduce the force, so originally it was at 53.8 pounds. By using our slider that we can see, we were able to get it down to 15.55 pounds.
For the braking system, we decided to keep the same system in the RV10, but made some modifications. One modification is to move the braking line to right up against your seat. This hinge here is what pushes the brake fluids. For our braking movement, we plan on using a movement similar to the hip abductor machine you find at the gym. Squeezing the right side will control the right brakes, and squeezing the left side will control the left brakes. We plan on connecting the hinge to the abductor movement. Van's aircraft didn't have any data on the force required to operate the brakes, but we estimated that the braking force that would be required would be around 25 pounds. In order to make sure that the weight of the APA will not affect the performance of the RV10, we have a table of weights and balances from Vans. The total weight of the aircraft must be below 2,700 pounds. Center of gravity must be between 107.84 to 116.24 inches after the datum. We assume that there will be no rear seat passengers or baggage. As you can see in this table, we are below the max weight and are within the accepted range for our center of gravity.
Our design was tested using the SimRailplane simulation tool, which has 4 control wires that are linked to the APA to test the different directions of motion. We needed to test the ergonomic feel of our system, as well as analyze if an aircraft could take off, land, and get out of stall using our controls. This project has expanded our knowledge about aircraft's control systems and the concepts of ergonomic engineering design. Overall, the work we've done as a team has shown us that the future of disabled pilots taking a seat in the cockpit without any obstacles is becoming a reality. We've enjoyed our time working with Jessica Cox, Patrick Chamberlain, and the Right Footed Foundation, as well as our mentor Dr. David Margolis. We hope that the project and the APA design helps pave the way for the future for armless individuals around the world.